Okay, let's go to see the other parameters. For example, if we go to edit parameters, reach, we will see some parameters of the in-channel or in-river processes. For example, the dimensions, which is really simple, the reach length, and the latitude and longitude. In this case, the latitude and longitude are 0 because these parameters are not used in this model. Then, if we go to the tab flow, we have some flow velocity parameters. These are just parameters that are describing how quick the flow is within the channel or within the river network.
Observed data?
That is calibrated. The exponent, so the 0.67, is pretty much the same. We tend to use the same value everywhere in the world, actually, because that's kind of a physical basis. But the the 0.04, which is the coefficient, it's normally calibrated.
So you haven't used any sort of EA data on flow or anything for the Thames Brook for this?
Yes, I've used the EA data, yeah. We'll see that later.
So that's gained from that previous stuff, which, and the graphs, those 3 graphs, I take it?
No, that's this value is calibrated by just comparing the observed flow and the simulated flow. We'll see that later. Then there is another tab called parameters. This is water quality parameters, so denitrification and nitrification. It's just processes that are happening to the nitrogen within the river channel. And then the last is effluent, which is very important because it's where we define the amount of flow that is being discharged into the river as an effluent, and its water quality, which is in the tab chemistry. So the amount of the concentration of nitrate and ammonium that this effluent has. Another parameter window is the subcatchment parameter window. So we go to edit parameters subcatchment and we open that. Here we have other characteristics. For example, in the subtab area we have the subcatchment area and the base flow index. The base flow index is a hydrological property of a catchment which describes the amount of base flow. The base flow is the flow, this is the slow flow, so the flow that is coming from the aquifer, the flow that is coming from the deep layers of the soil, and is usually what is forming the low flow. When you observe flow in the river, but it has not rained in the last week, like for example right now, it has not rained in the last probably 10 days, or it has rained very little, but there is still flow in the river. It's because there is base flow. So when the base flow is 1, base flow index is 1, we have only base flow in our river. When it's 0, we don't have any base flow. So if it doesn't rain, we don't have water. Then other tabs are, for example, direct runoff, where we have some parameters that describe the generation of flow in the surface of soil. So it's basically the amount of rainfall that is not infiltrated into the soil, but it's just transformed into runoff. Then we have a tab called deposition. So here we have the deposition you asked before. Here we have where you set the values. So we have nitrate dry deposition, nitrate wet, ammonium dry, and ammonium wet. Normally you have literature values of this. It's not difficult to find on the internet or in books values of nitrogen and phosphorus deposition. Normally you don't find that divided into dry, wet, nitrogen, ammonium, but that doesn't matter because Inca sums them all together. Then we have groundwater parameters. For example, if we go to groundwater tab constants, we have the residence time, which is set to 15, which is the velocity of the base flow of the groundwater. Base flow is more or less a similar concept. Groundwater is when it is in the soil, in the deep layers of the soil, and base flow is when it is already into the river. So this is it's a residence time, the same concept as we have seen before, but it's referred to the groundwater. And And then we have another important tab, which is landscape units. Here it's where we define the percentages of land use. So for this reach, in this case we are displaying reach number 8 within stream number 4. We have 10% of forest, 25% of improved grassland, and 65% of urban land. And in the left part of this window, where you have some numbers, you can select the stream and the reach, or the stream and the subcatchment. For example, if you select the stream number 1, you will open out 4 subcatchments, and it's the subcatchment 3, 4, 5, and 6. And so if you select number 6, you will see that we have 99.01% of urban and 0.99% of improved grassland, which was the catchment that was not correctly displayed in the window at the beginning. And just to end with the parameters, you've seen that here and there you have something that is called initial values. For example, you have it if you still have the subcatchment window open, if you click on groundwater parameters, you have a tab that is called initial values. These are the initial values of flow, nitrate concentration, and ammonium relative to the groundwater. But then you have some other initial values, like initial values of soil water, of nitrate in the soil water, of water in the river channel, etc., etc. This is because the model needs to be initialized. It's because the model is predicting, for example, the amount of flow and the nitrate concentration, the ammonium concentration into the river. But in order to do that, it needs to start from a starting point. So the initial values are also quite important. And there are several ways of estimating them. You can just put average values, made up values, and then calibrate them. You can use observed values. So if you know that at the beginning of your simulation period you had 2 cubic meters per second in your river, you write that. Or that's the way you normally do it.
So with the groundwater, would you include like contaminated land as potentially affecting groundwater?
What do you mean exactly?
Because like one of the sort of unknown things, particularly within, say, the Lee Valley, is you've got a lot of contaminated land, and it's like historic contaminated land, and there's certainly thoughts that, there's stuff leaching out of them.
Mm-hmm.
I mean, there's not that much evidence of it, but I was wondering, like, how would you consider that within? Would you consider, is the groundwater, because at the moment within the Lee Valley it's all clay with gravels.
Yes.
So minor aquifers.
Actually, the base flow is 0.29, which is a low value. The whole of the Thames is 0.7.
Yeah.
So that gives you the proportion.
But I was wondering, like, would you potentially include
For the nitrate, I don't think it's a huge problem, although I might be wrong, so that we should check out if that is true. It would be a problem, depending on what that contaminated land is leaching, which I don't know what that is, but if we wanted to consider that, I'm not sure, I'm not aware of any Inca application in a context like this, so I don't know if that has been done before with this model, but I suppose you could try and do that by setting the initial values of a given contaminant or a given variable very high, and see how the model is reproducing the release. There's no release.
Make a whole subcatchment with contaminated land.
Exactly. Yeah. Sure. Yeah. And I have to say that Inca is not used in this kind of remediation studies because there are very detailed groundwater models. While Inca has groundwater in Inca is just a component, and it's coded in a very simplified way. While if you want to do that in a very detailed way, you have very complicated models that instead, for example, instead of having like one element for the whole contaminated subcatchment, you may have like 100,000 like squares or triangles or whatever, depending on the type of model, and you have these finite volume models that are
So
very
don't do
detailed.
that.